Hi everybody, hope you're doing well. Now that we discussed a lot of the mathematical ground, Hilbert spaces and all that, we are in a position to discuss quantum dynamics. To do that, first I will discuss something related to complex numbers. So let us start discussing complex numbers evolving in time. Okay? Suppose you have an equation of the following form: a derivative with respect to time of a given complex number, which is just a function of time for the time being, right? And it is equal to I omega with a negative sign here. I'll put a negative sign here, and it multiplies psi of the time t. So I want to solve this equation here, this form of equation. Suppose this is just a complex number. So psi is in the complex numbers. It is in the set of the complex numbers, and omega is just a real number for now. All right, it's just real. You can plug in a complex number in general here, but you'll find that the time evolution of this complex number will not only rotate in the complex plane, but also will dilate eventually or contract. So that's not what we want. We want this omega to be real here. All right? So let's go. This equation is very well known, and solution to that is just of this form: psi of time t, the argument, the time evolution of this corresponds to just a constant, a complex number, say, and multiplied by minus I omega t, the exponential of minus I omega t, all right? So this is the solution for the previous equation, all right? And what does that mean? Well, first, if you take the derivative of that, you'll find that psi 0 is just a constant. So psi 0 is a complex constant in time with respect to time. Right? With respect to time, this psi 0 is just a constant. So we need to apply the differential operator to the exponential. And we already know that differentiating the exponential, just repeat the exponential, and the constant multiplying the variable here goes in front of all the equation. But now this is just psi. So in this case, the differential equation is completely satisfied. But what is the meaning of this thing here? All right. Well, if you look at things in a complex plane for complex numbers, if you look at a complex plane, you'll find that real axis here, the imaginary axis here. So you'll find that at time t equals to 0, you'll have psi of 0 here. The initial time will produce just this number, psi of 0, subindex 0 here. And it's a complex number. It has a real part and an imaginary part. and it can be, so the real parts here and imaginary parts be here, and this can be put in the form of modulus. So modulus of psi 0 and the initial phase, say phi 0. So this is the initial phase, and this is the modulus, the size of this complex number here. So we already know a complex number has a modulus, which is equal to the square root of the sum of the squares. So that's it. And when time moves forward, when time passes, this number evolves rotating. It just rotates in the clockwise sense. It's a clockwise rotation because this minus here. So the number is just psi of t is equal to psi 0 modulus, the initial phase, I to the exponential I phi 0, and minus omega t, right? For any other instant of time, just multiplying this thing by the complex psi 0 in this form, in the polar form, all right? So the number, this function here, rotates in the complex plane. So in a given instant of time, it will be here, and it rotates with an angular frequency omega. All right, this is the angular frequency of rotation of this complex number in a complex plane. And if for omega not in the real numbers, if it's not a real number, it can change the size of the vector. But we are not interested in non-real values for omega. Omega is just a real number for now. So this complex number will rotate, keeping its size, its length constant. So the modulus of this function is just equal to the modulus of this constant here, which corresponds to the initial value of the function. All right? So it rotates in a complex plane, just changing phase, not modulus. The length or the size of this complex number is preserved. All right? So that's that's the content, the mathematical content of that equation. Just let us summarize. So d psi dt is equal to, I can eventually put the imaginary unit here, but let us continue to write imaginary here. All right, imaginary unit. Minus I omega psi, this equation, has a solution. Solution psi of t is equal to psi 0 e to the minus I omega t, right? Omega is in the reals, in the real numbers, so has a solution which just rotates, right? Just rotates in a complex plane with angular velocity or angular frequency omega, keeping size, the size of the, or the length of this function, or the modulus, preserved. All right, it is preserved. It does not change. The modulus is a constant. All right, so That's what we have for now. Now, let's go to quantum mechanics. All right, let's try to understand what must be the case in quantum mechanics. So, let's go for a Hilbert space where vectors are complex vectors. So, in quantum mechanics, physical states are represented. It's just the postulate of quantum mechanics by a psi in Hilbert space. And also, there is a norm imposing, there is another postulate imposing that the norm of the state must be equal to 1 because of the probabilistic interpretation. So given psi, what is the probability of measuring psi? It's the modulus squared of this number, but since it's projected onto itself, and the projection of a vector onto itself in Hilbert space is a positive definite quantity, this thing must be unit. All right? So in quantum mechanics, physical states are represented by that psi, and this condition must be always satisfied. So what if I want to calculate some psi of an instant of time t projected onto that same function in a given instant of time t? All right, what really must happen here in quantum mechanics? Well, this also must be equal to unit, the one in the right hand side. It cannot be another thing but a one. All right, so let's try to consider an evolution operator. In quantum mechanics, all the things must be represented by operators. So let's try an operator here, right? So say, for instance, that psi of a given time t is equal or must be equal to some operator, some I am writing in a u here, you'll see why is that, some operator, an evolution operator, which takes the function from 0. You can plug in another time t subindex 0, the initial time, but I'll write 0 for the time, the initial time here. So it applies to the function at the initial time 0 here. All right, I'll write it just this way: u of time t, because we are just considering 0 here, so I'll drop that from the notation. And this is the initial state. So this is the evolved state, and this is the initial state. And this thing here, this operator here, is called the evolution operator. All right? But now I can ask, what are the properties of the evolution operator? What properties does that object does the object have in order to be an evolution operator in quantum mechanics? All right, let's make use of the probabilistic interpretation, but also the important consequence that you are interested in preserving the norm of vectors in the Hilbert space. All right, so psi of t projected onto psi of a given instant of time t must be equal to. Now I can plug in here the initial state, the bra state, the initial u dagger of time t. So remember that psi of t is equal to the evolution operator operating on the initial cat state in Hilbert space. So if I take the complex transposition here, I'll get the bra, and the bra just corresponds to the bra of the initial state and the u dagger here, all right, at the instant of time t. So this is the bra at time t, and the cat at time t, I can write it as a function of the evolution operator operating on the initial state here, all right? These are operators, so I'll put a hat above the letters. So just to remember you, they are operators, all right? So they are quantum mechanical operators. And from the probabilistic interpretation, this must be equal to unit, the unity, all right? So when vectors in a Hilbert space don't change the size, don't change the modulus, this value here at a given instant of time must be equal to 1. So is the initial vector, all right? It is equal to the initial vector, the initial state. So this thing here, the evolved state, projected onto itself, has a probability of 1, which is equal to the initial state. So saying in the quantum mechanical language, given the physical state psi 0 at the instant of time t equals to 0, what is the probability that I can measure that state? Given that state, it's 100%, it's 1, right? But time passes, it evolves in time, this state evolves in time. So at another instant of time, at time t, given the state psi of t, what is the probability of measuring that state? It is also 1. So notice an important conclusion. Time evolution does not change the norm of cats and also the bras, does not change the norm of the cats in quantum mechanics, right? So it must be a rotation in Hilbert space, a complex rotation, all right? Because we know that a given vector, if you rotate the vector, it is in another state, it is rotated with respect to the initial vector, but its length, its size is preserved, all right? So time evolution in quantum mechanics must be produced by something which is a rotation in Hilbert space, a rotation in a complex vector space. So in order to keep that identity, which means projective vector onto itself must be a constant, which happens to be 1 in the probabilistic interpretation of quantum mechanics, must correspond here to something in order to have this equality, and this something here must be just one thing, the identity matrix. All right, it must be the identity matrix. This product here must be the identity, because it is the only way I can find that this thing here, evaluated at time t, is equal to this thing here, evaluated at time t equals to 0. All right, so this thing here must be the identity matrix, because if that applies, the identity multiplying the initial vector is equal to the initial vector. Identity is just produce the same thing when applied, and the equality holds. All right? So this evolution operator in quantum mechanics must be equal to unity. That's a very important fact. So in this case, we must conclude that u dagger of time t multiplying u of time t must be equal to the identity, which means u dagger at time t of the evolution operator must be equal to the inverse, because it's the only way when you multiply a matrix by another matrix, it is equal to the unity or the identity matrix. Is just when this matrix here, which is in general distinct from that one, it is, in fact, it is the inverse. So the time evolution operator has the important property. Evolution operator is given, or is, must be, it's better to put that way, must be unitary. All right? This is for unitary operators or unitary matrices. Unitary matrices, the inverse is equal to the transpose conjugated. All right? So the transpose conjugated, when it's equal to the inverse of a given matrix, that matrix is said to be unitary. We already talked just a little bit about that. So evolution operators must be unitary. Now remember that physically observable quantities are represented by Hermitian operators, which corresponds to those matrices for uh, for whom the transpose conjugated are equal to itself. They are self-adjoint, say. So observables are Hermitian, and evolution operators must be unitary. This is another postulate of quantum mechanics. The evolution operator must be unitary. It can be raised to the status of a postulate. It is just a consequence, perhaps, of the probabilistic interpretation. But also, if you drop out the probabilistic interpretation in quantum mechanics, usually in another interpretations, it also holds that evolution or coordinate transformations must be done by evolution, by unitary matrices, by unitary operators. All right, this is a postulate of quantum mechanics. But now, for now, we are interested in time evolution. So in time evolution, time dynamics, the time evolution operator must be unitary. All right, it's a very important consequence of the postulates of quantum mechanics. Is another postulate, or maybe it's a corollary of a probabilistic interpretation in this case. But the time evolution operator must be unitary, all right? Now, I must remember the following thing. Unitary operators, unitary matrices, always can be written as the exponential of a Hermitian, all right? If you express a unitary matrix this way ensures the unitarity, all right? This form of the matrix ensures unitarity. A unitary matrix is always can be expressed, at least I don't know any counter example for that matter. It's the exponential of the imaginary unit multiplying a Hermitian matrix or a self-adjoint matrix, right? Or a self-adjoint operator. But now let's remember the first thing we did. For a complex number, what is this unitary operator? If you want to keep the modulus of complex number, a complex number satisfy an equation of this form. Sorry, my dog. Well, I'm back. So for a complex number, the time derivative of a complex number must be equal to this thing here, and this thing here ensures that psi of the time t, it's evolved, all right, is equal to the initial state, all right. I will write it, the exponential in front of the initial state, so you can see the analogy. It is multiplied by the exponential of minus I omega t. So this thing here, when talking about Hilbert space, this is for a Hilbert space of dimensionality 1. It's a complex space. It's just a complex number. So the unitary operator here is just a complex number. It is e to the minus I omega t, all right? That's the time evolution operator for a complex number rotating, just rotating in a complex plane as time evolves, as time goes into the future, all right? Modulus is preserved, and the number just rotates in a complex plane, all right? So we can generalize that. We can generalize that by writing. Remember that to keep the norm preserved, I need a unitary operator, which is a matrix of dimensionality n, which is the dimensionality of the Hilbert space. And this matrix must be unitary. It must preserve the norm. So it must have something to do with this thing here. So what I can do to consider a time evolution operator in quantum mechanics, I can write something like this. Unitary operator, it just rotates. So it must be a matrix. By analogy, I'll put a minus here, I, a matrix omega multiplying the time t. All right? It's a matrix. containing frequencies of rotations. If, for instance, you have a psi in some sense in a diagonalized basis, you have 1 here, 2 here, an alpha state here in Hilbert space, an n state here, so the dimensionality of the space is n. You have lots of directions in the space. And this vector, psi vector in Hilbert space, remember just a pictorial image of what is happening, this thing must rotate. And rotation here corresponds to multiple axes. So there must be given, there must exist a matrix of rotation or of angular frequencies. And these angular frequencies are written here. Notice that this form of the matrix of the time evolution operator here is just the exponential of the imaginary unit multiplying a Hermitian matrix. And this Hermitian matrix here is just minus omega t. Well, if this thing changes with time, in some limit you can have a changing in time frequencies. So it will be an omega integrated over the t prime here from 0 to time t minus. But for the sake of simplicity, I'm considering a constant omega matrix. All right. So this produces a consequence, an immediate consequence. Time is a real number, and for a dagger, which is the transpose conjugated of A equal to A, you have minus omega dagger multiplying the time t, and this omega dagger must be equal to omega. So omega, the matrix containing all the natural frequencies of rotation of the system, of the quantum evolution, must be given, or the frequency matrix must be given by a Hermitian matrix. All right? So, it's a very important conclusion. An evolution operator must be given by something like that, which corresponds to just rotate the state vectors in Hilbert space, but does not change the size of the vector. I need to emphasize here that's just a pictorial view, because each component projected to all the axes here, to given axis, for instance, the one axis, it will correspond to a complex number, so it rotates internally and rotates in the directions here. Say psi1, it's a complex which rotates. If you remember, this is a complex number, so it rotates internally. This axis here just corresponds to a real and imaginary axis. This also has a real and an imaginary axis and all that. But overall, the vector does not change its size. It does not change its modulus. It's given by this thing here. And the frequencies, the matrix having as eigenvalues all the frequencies of the system, must be Hermitian, which means the frequencies are real. They are real numbers. So let's consider another thing here, right? We concluded that omega is equal to omega dagger. It is the generalization of omega is equal to a complex conjugate omega, which means omega is real in the case of a single complex number, and you just rotate the complex number in the complex plane, but does not change its size the generalization corresponds to this thing. So rotation matrices, and the rotation here is rotation in the complex space, in an abstract space of the Hilbert space. Say this matrix produce rotations as time evolves, as time passes, and this as time goes forward into the future. All right, it's better to say it that way. So these matrices here are emission, which means eigenvalues are real of the omega here. Eigenvalues real. All right. So for a single complex number, only one frequency, which is real. For complex vectors rotating in Hilbert space, which is a complex rotation, they are given by unitary matrices, and these unitary matrices have the property of being written as an exponential of a Hermitian matrix, which implies that the frequency matrix, the matrix containing all the frequencies, must be Hermitian, which means the natural frequencies are real. The eigenvalues of this matrix is real. All right? But now let's remember another concept in quantum mechanics, which is Planck, Planck relation. For a single frequency, we have energy is equal to h bar multiplying omega, which means a single frequency is just the energy divided by h bar. And if we are interested in a system which has multiple energy states, it must be represented by a matrix. This matrix is called the Hamiltonian of the system, and the Hamiltonian of the system corresponds just to h bar multiplying a frequency operator. All right. So generalizing relation, Planck's relation for a single frequency related to energy here, we can remember that energy is represented in classical mechanics by a Hamiltonian function, and this Hamiltonian function must be replaced in the quantum world by a Hermitian operator, which is the Hamiltonian, which contains all the eigenstates of energy of the system, and this must be written by Planck's relation, as a consequence of Planck's relation, as h bar multiplying an omega matrix. All right. So I can isolate this omega here. I can isolate that and write in the following way. All right. Omega, which corresponds to all the eigenfrequencies of the system, is just given by all the eigenenergies, which are represented by the Hamiltonian operator, divided by h bar. So this is the Hamiltonian operator. All right? And this way, the unitary evolution operator is just minus the imaginary unit, the Hamiltonian operator divided by h bar, which is just the frequency matrix, multiplying the time t. So suppose for now that h, the Hamiltonian, is time independent. All right? For the sake of simplicity, if you have a time-dependent Hamiltonian, you just replace that by some integral of h over dt from 0 to time t, dt prime here, and divide this by h bar. So it can be demonstrated, this thing here, but Now, for the sake of simplicity, just consider a time-independent Hamiltonian, all right? That does not change what we want to demonstrate. Even if Hamiltonian is time-dependent, the equation which will follow is the same, all right? So remember, time evolution is given by something like this thing here, all right? What this thing does to a state in Hilbert space, it complex rotate this state. It's a complex rotation, all right? It preserves the norm, but rotates the state. So now psi of time t is equal to the evolution operator, which we, by induction, demonstrated to be a thing like this, right? Remember, rotation of complex numbers, rotation of a complex number. By analogy, psi of t is equal to exponential of minus I, energy, a single energy divided by h bar, multiply t, it is just a frequency, multiplying the initial state, the initial position in the complex plane. So a generalization, it's for a vector. You have a matrix of exponentials of frequencies. All right, this is an exponential of a matrix containing frequencies multiplying time, and this is the generalization of just a complex number. It's a complex vector, right? So a complex vector evolved to time t is just a complex vector at time t equals to 0 multiplied by a unitary matrix, which produces complex rotations. All right. Now it's just it's more than just a rotation in a complex plane. It's a rotation in the Hilbert space. All right, which is a complex vector space. Well, now I wanted to know what is this thing here. What is the time derivative of the function psi of t? What is the time evolution of this thing here, right? And I can do the math here. I'm just applying the differential operator. It just operates on this thing here because there is a constant. It's just the initial state, and this just produces the constant matrix here multiplying time. You can write a Taylor series for that thing, differentiate, but this matrix commute with the exponential because the exponential is just a function of the matrix. So you can readily apply the same rules as for the derivatives of scalar exponentials or pertaining to complex. This is unitary pertaining to some unitary group, but you can derive, you can differentiate it. It's just this thing goes in front of all the things. This is just h bar here, and the exponential repeats. So same rules apply. And this is a psi 0 here. And this thing here is just, again, the initial state. So we have found the equation we are interested in. All right? We have found that equation. That equation will be just the derivative of psi of time t with respect to time t is equal to minus I, the Hamiltonian divided by the h bar, multiplying the function of time t. And now we can multiply all the equation by the imaginary. So the imaginary here, imaginary squared, you'll get a -1, but this minus cancels out. The h bar, if I multiply all the equation by the h bar disappears from here, and I'll find that d dt, time derivative of a given state in Hilbert space, which corresponds to state of the system, is equal to the Hamiltonian multiply psi of t. This is Schrodinger's equation. All right. So it just relates to rotations in a complex rotations in a complex space, which is Hilbert space. So this is called usually the time dependent Schrodinger's equation. All right. What we have learned so far, it can be raised to the status of an postulate in quantum mechanics. Time evolution of a quantum mechanical system or quantum dynamics is described by Schrodinger's equation. And this equation just implies that your time evolution operator is unitary, which just implies that the state vectors don't change the size, don't change the modulus, all right? Which means, given some state at the initial time t equals to 0, the probability of finding that state, given that state, is 1. You already tossed the coin, so you already know what it gave as a result. And given that state at the initial time, at the same time, the probability is always 1. All right? So what is the probability of an event given that event? Is 1, right? So the size of the state vectors in quantum mechanics must be preserved. As a general fact in quantum mechanics, transformations, right, in general, not just for time evolution, in general, if you have a psi state and you want to transform it to another frame of reference, you can perform a transformation, an S, applying a matrix S to the state, and given a psi seen in the previous frame of reference, given psi, what is the probability of finding psi? It's 1, so this state vector must be normalized to 1. And in the new reference, this thing must also be equal to 1. So transformations, as just there is, I guess, just one exception, which is time reversal symmetry. But in general, there are exceptions, I must say. But then the transformed state gets a sign. But there are exceptions. But we are not interested in those exceptions right now. This must be equal to that, and the transformed state psi prime, which is the psi s dagger here, the psi prime here is s operator on psi, operating on psi, which is equal to the same thing here. It must correspond to the unity, the identity, and the identity in this case it must correspond to the symmetry transformation or the similarity transformation in general must correspond to a unitary transformation. So basis transformations, they must be given by unitary transformations. Unitary transformations means when you change basis, when you change frame of reference, when you evolve things in time, a state projected onto itself reserves norm. It's equal to unity. And this must be done by applying symmetry operators or evolution operators, which are always or almost always, there are exceptions, as I told you here, by evolution, by unitary transformations, by unitary operators. All right, so transformations are unitary in quantum mechanics. Physical observables are Hermitian. It's an important fact in quantum mechanics. So in general, for transformations like that, this transforming operator here, the transformation operator, this matrix, must be unitary in general, with a few exceptions to that rule. Time reversal, I guess, is one exception. But let's do some other calculations in quantum mechanics. So if you replace the function by the evolution operator here, multiplying the initial states, this is just the psi of time t. It's equal to the Hamiltonian, the evolution operator, and the initial state psi 0. This equation just shows you that it doesn't matter what is the initial state. All right? You have an equation for evolution operator. And the equation for the evolution operator is the time derivative of that operator, which is the evolution operator, the function of time, is equal to the Hamiltonian. Now I'm writing it as a partial derivative because the Hamiltonian can, here I would replace eventually the time derivative, the total derivative, by partial derivatives, because this can include also spatial derivatives. So the Hamiltonian applied to the evolution operator here. So this is the evolution of the time equation for the evolution operator. And solution we already know. It's just the exponential of minus I, the Hamiltonian, divided by h bar multiplying time t. Or if this is an operator which depends on time, you can multiply everything by the dt, divide by the operator u, is the inverse of the operator, and same things as for um, ordinary equation, differential equation of order 1. You can apply here and you'll find out. But we already have the solution for this equation here. All right, so it's just the time evolution of a quantum system. It's described by this evolution operator, which is unitary. All right, I I am repetitive, perhaps, but it's very important. It's very important to keep important things in mind. So I repeat the important issues here. All right. Well, now I can provide a few examples. For instance, suppose, or you can ask, what happens for an eigenstate of the Hamiltonian? What happens if I plug in to the equation an eigenstate of the Hamiltonian? So say this is an eigenstate of energy with energy E. All right. So for an eigenstate of the Hamiltonian, if you apply the Hamiltonian to one of its eigenstates, say a psi, which is an eigenstate with energy E, say this state, say this thing, an eigenstate of energy. I'll use the redundant convention, all right? It produces the eigenvalue and repeat the eigenvector, right? For an eigenstate of the Hamiltonian, when you apply the Hamiltonian to an eigenstate of energy, it gives you the eigenvalue and repeat the eigenstate, right? The eigenvector. So if I put psi is equal to that, a given eigenstate of energy, what happens? Well, I, h bar, the time derivative of psi of time t, it's just the psi 0 here. I plug in an eigenstate here, differentiated with respect to time t, is equal to the Hamiltonian applied to psi of t, all right? And this psi of t can be written as a phase, say, exponential of minus I omega t, which is just the energy divided by h bar, as we will see right now, multiplying the eigenvector, which is an eigenstate of the Hamiltonian. So notice what happens. When this is an eigenvector of this thing here, you'll find out what? You'll find out that I, h bar, time derivative of psi of t is equal to the energy E corresponding to that eigenvector E, multiplying psi of t here, and this can be readily integrated. It is just, well, you can demonstrate that. All right, can demonstrate E to the minus I energy eigenvalue divided by the h bar multiplying time t, multiplying the initial state, which is the eigenenergy state, the E here. So a system in an eigenstate of the Hamiltonian with an energy eigenstate, it just changes by a phase factor. It does not really rotate in Hilbert space. It just rotates somewhat rotate in the complex plane for that direction, but it's just a phase, all right? It's just a phase. Changes eigenstates of the Hamiltonian just change by a phase factor. So what is this phase factor? Exponential of minus I, the energy of that state, the eigenvalue of the energy, divided by the h bar multiplying time t. So in Hilbert space, the vector is always in the same direction, which is this direction here, but the amplitude, which is always in modulus equals to 1 in that direction, changes by a phase, just a phase factor. This is a phase factor. All right? It's a very important thing. And this, when you find the eigenvalues of the Hamiltonian, this is called the Schrodinger independent equation, time independent equation. So the time independent equation Schrodinger's equation corresponds to finding these vectors, the energy eigenvectors, right? For which psi of t, for which psi of t corresponds just to a phase factor multiplying one of the energy eigenstate, the eigenvalue of that eigenstate. All right. So for uh, for an eigenstate of the Hamiltonian, you have just phase. All right. It's very important. So when you want to find out the eigenstates of an atom, you need to find out solutions for this equation, this Schrodinger equation, which is time independent. You are trying to find out what are the eigenenergy states or the eigenstates of energy, right? You solve for a Hamiltonian which has in it potential energies, kinetic energies, and when applied to an eigenstate of it corresponds to an eigenenergy, to an eigenvalue of it, multiplying that eigenstate. All right, it's a very important application of Schrodinger equation. The Schrodinger equation. Well, just to finish, I must talk about averages of operators and something called the Heisenberg picture. All right, so averages of observables. In the end, what you really want to know is this thing here, because the state psi in Hilbert space is not a direct measurable quantity. So you need to measure operators, observables, physical observables. And in this case, for a single measurement, you just find out an eigenvalue of that operator. But you need to repeat measurements to find out averages. And this is very important. It's a very important issue. Suppose you have an observable O. It must always be Hermitian. The Hermitian. Hermiticity of an operator or the self-adjointness of the operator ensures it has only real eigenvalues. That's a very important thing. And suppose, for the sake of simplicity, this operator does not depend on time. It's just a constant in time. It's just constant in Schrodinger. O is constant. It's independent of time in what is called Schrödinger's picture, the Schrödinger version of quantum mechanics. So what I need to do, I want averages of these operators at time t. But at time t, the average of that operator corresponds to the state of the system at time t projected, or the operator is sandwiched between the bra of the state at time t and the cat of the state at time t. It gives you the average of that matrix. All right, it gives you a number which is the average of the operator of it can be a component of the momentum or a component of position or component of the angular momentum or the electric charge eventually, or anything you want. So this is the average at time t. All right, it's the same as the average at the initial time. I say it's the same definition. You just project states here and put the matrix in between. So it's called in the jargon sandwiching the operator. So you have a bra, the operator here in the middle of your sandwich, and a get there. All right. So you calculate at time t just projecting with this thing here, this object which is evaluated at time t. Suppose in the Schrodinger picture, in the Schrodinger version of quantum mechanics, it is the physical state which is evolving in time. So the operator is time independent, but the average is time dependent because the state is evolving. So the state is changing. All right. So this is the nature of the time evolution of operators. So you want to calculate the averages. Now look at that thing. The average of an operator with respect to time t is equal to the physical state, which is the psi zero, the instant of time zero. U dagger, the operator is here. So this is just the state of the system evolved in time. This is the time evolution operator. And this is the state, the cat state. This the initial state evolved by the evolution operator, which is unitary. All right. And now, since matrix algebra allow us to do that, we can put the initial state here and multiply first the unitary evolution operator by the observable we want to calculate the average, and multiply these things this way, and to finish the initial state there. All right. So you can call now it as a operator depending on time, because this is time dependent. This is not time dependent, but when you multiply things here, you'll find out an object which is time dependent, and this is what is called Heisenberg picture. This is the Heisenberg operator. Let us put a sub index here with an age here. Just remember Heisenberg, which first derived this equation, I guess. And this is the Heisenberg's picture. All right? Heisenberg, contrary to Schrodinger, puts all the evolution onto the operators, right? Schrodinger, for Schrodinger, an observable, if not explicitly dependent on time, is independent on time. It does not depend on time, right? So operators doesn't do, let's say operators don't depend on time, and all the time evolution is in the physical state, in the cat states, or in the block, all right. But for Heisenberg, all the evolution is in this object, which are the operators. The operators evolve in time. So for Heisenberg, it's just to try to understand what happens by analogy. It's just that a similar situation where you can think about, well, in one version, the Schrodinger version, You have the physical state here, which is a vector in Hilbert space, to be precise. But suppose it's a vector in here, just in three-dimensional space. And Schrodinger's picture, the vector rotates, all right? The vector rotates. The state rotates. And the coordinate system is kept fixed, all right? The coordinates here are, in fact, the operators. But suppose that for Schrodinger, the states fixed, states rotate. Schrodinger rotates states. For Heisenberg, states are kept fixed. The initial state is forever the state of the system. It does not rotate on Hilbert space. But to ensure that the averages in both pictures gives the same answer, because if it does not apply, it's nonsensical, all right? For Heisenberg, states fixed, but things which I want to measure rotates. The coordinates, suppose, or the operators rotate in Hilbert space. And so, to summarize, Schrodinger's picture states the physical state of the system. The psi is a function of time. It rotates. And the operators are kept fixed. For Heisenberg, the state does not rotate, but the operators must be rotated to produce the same answer, which is the average of that operator as time evolves. All right? So it's a very, very interesting thing in Heisenberg version of quantum mechanics that an operator for Heisenberg is just evolved in time by applying the inverse evolution operator of the Schrodinger evolution, right? And by from the left here, you apply the U dagger. The operator is in between two matrices, and this is the evolution operator. So for Heisenberg, you must pick the Schrodinger operator and then sandwich it with evolution operators. But here is the evolution operator, and here is the inverse of operator. And this operator, we already know it is just minus I, the Hamiltonian multiplying time divided by the h bar. This is the evolution operator. All right. So if you want to calculate the time derivative, of a Heisenberg operator, well, you'll calculate this derivative, the operator here, the u there, plus u dagger, the operator here, time derivative of that. But remember, u dagger is just a change in sign for the imaginary unit. So when you differentiate that, you'll find that here you'll have u dagger, and the derivative produces an I over h bar, the Hamiltonian. The u dagger will multiply O and multiply u again. So you'll find the Heisenberg operator here again. And there you'll find a minus I over h bar, which is just a scalar constant, but it's complex, but it's a scalar. U dagger O, the Hamiltonian appears here. It commutes with the unitary evolution operator, but U dagger O U is just a Heisenberg operator again, and the Hamiltonian appears on the right side. You cannot commute these things because you don't know if the operator commutes with the Hamiltonian. You don't know that. You don't have previously or a priori to know. You don't have to know if they commute. But if they commute, they are just compatible, or if they don't commute, they are incompatible. So it appears right here. You can now multiply everything by I h bar. So you can multiply the equation by I h bar. So do that. Multiply all the equation by I h bar here. So you'll find I h bar, the time derivative of an Heisenberg operator, is equal to, when you multiply the imaginary for the minus imaginary here and the h bar, it cancels out. This keeps it goes to a positive number. This comes to be negative, and you find a commutator. You can easily demonstrate that. So you'll find that the equations of motion for Heisenberg operators state the psi of the system, the vector, the cat state of the system is fixed in Heisenberg picture, but operators evolve in time according to this thing here. This is called Heisenberg equation of motion. If the operator has an explicit dependence on time, for an explicit dependence on time, you have also to calculate the derivative of this thing here, and you'll find out that you have to introduce this object here. The time derivative of the operator, which is explicitly time dependent, u dagger time derivative O u, but in general you can assume, not always, but in very important cases, this thing is here, is zero, is not explicitly time dependent, so you can drop out that term from the equation, and this is the Heisenberg equation of motion. And this has a direct connection with classical mechanics. So remember, we just reviewed in brief classical mechanics. You have a time derivative of a given operator, a classical operator, is equal to the Poisson bracket of that operator with the Hamiltonian, a Poisson bracket here. So again, Dirac, I remember you again, Dirac pointed out that from classical to quantum, replace Poisson brackets by, if you want to keep the time derivative alone here, you must replace this object, which is a Poisson bracket, by a commutator, but divided by one, divided by I h bar. All right, that's replacement, which Dirac pointed out. You can find a very similar situation between classical mechanics and quantum mechanics, but you need to replace Poisson brackets by just commutators. All right. So Heisenberg equations of motion, the Heisenberg equations of motion are, or can be, very useful to quantize systems. All right. That's a very interesting connection between things. So there are two point of views, and there are other possibilities. I will not talk about that right now, but there is something called interaction picture. All right, the interaction picture is a mixture, is a mixed picture. Something evolves with Schrodinger's equation, and other things evolve according to Heisenberg equations of motion. But I'll not talk about right now. You can find out in Sakurai. I recommend lecture, chapter 2. Modern Quantum Mechanics, the Modern Quantum Mechanics by Sakurai. You'll find out all the discussions we have done here. But to summarize, let us summarize a little bit. Schrodinger picture, all right? Psi is a function of time. It evolves according to an evolution operator. And so satisfies Schrodinger's equation. And averages of operators are functions of time, but they are psi of t. The operator is invariant in time, usually, and you must calculate these things here. In Heisenberg, picture, psi of the time t for Heisenberg is always the initial state, all right? Schrodinger puts all the evolution into the cat state. Schrodinger and the operators are kept invariant, usually unless they have an explicit time dependence, all right? So when they have explicit time dependence, you use some mixed picture between these two distinct and radical opposite views, which are Schrodinger's. In Schrodinger, states rotate in Hilbert space, and the operators are kept invariant. For Heisenberg, operators change in time, but state is fixed in the Hilbert space. So for Heisenberg, a given state is always the initial state. It does not evolve in time for Heisenberg. For Heisenberg, states do not evolve. For Schrodinger, all that evolves is the state. For Heisenberg, no, states kept fixed. All right. But operators for Heisenberg evolve applying the evolution operator. So if you do that, the evolution operator is the same in both pictures. So in one scenario, you apply the evolution operator to the physical state, in the other to the physical observables. And in this case, you'll find that the time derivative of operators, the Heisenberg operators, satisfy a commutation relation with the time derivative is equal to multiplied by the IH bar. The time derivative is equal to the commutator of that Heisenberg operator commuted with the Hamiltonian of the system, the energy matrix, say, of the system. All right? But Heisenberg has another advantage with respect to Schrodinger. In Heisenberg picture, I have this equation. And things that does or things that don't change in time, things that don't change in time have total derivatives equal to 0 with respect to time. So conserved quantities, say conserved operators, I don't know if you can read this thing here. It's really a mess right now, but finish. Remember, you can talk about conserved quantities. If something is conserved, time derivatives are equal to 0. So for conserved quantities, the commutator of the Hamiltonian with that operator, which is a conserved quantity, must be equal to 0. That way, time derivative of that operator is 0, and that quantity, that physical observable, is said to be conserved. All right? So if angular momentum has to be conserved, or some component of the angular momentum must be conserved, the commutator of that operator with the Hamiltonian must be 0. If it's distinct from 0, it does not commutate. They are incompatible observables, and that quantity evolves in time. It's not conserved in time. All right? So for conserved quantities, the commutator of that observable with the Hamiltonian must be 0. They must commute. Which means, by the way, that the bases which diagonalize the Hamiltonian, the energy eigenstates of the system, are also eigenstates of that operator. All right? It's a very important conclusion here. Well, I finish here. I hope it's more or less clear what I was trying to talk about. And I'll see you next time. Thank you.